Alright, so these notes are on the kinds of stars. We'll go over 8 different kinds of stars. Those aren't the only stars that exist, but these are the more common stars that exist in the solar system. And you might be asking yourself, why are we talking about stars? That's not chemistry. But a couple years ago, they deleted Earth Science as a class. So when you came in, chances are that you started with biology, but back a while ago, it used to be you started with Earth Science unless you tested into biology or advanced or gifted or something. And now what they did was, instead of just deleting Earth Science, like, oh, nobody takes Earth Science, they want the other classes to absorb some Earth Science. So I teach a little bit of Earth Science in biology. This is a bit of Earth Science that we're going to cover in chemistry. And when you get to physics, you're supposed to cover things for some Earth Science as well. That way, by the end of high school, you've absorbed a lot of that Earth Science information as well. So we need to know the types of stars and then also the life cycle of stars, focusing on fusion and fission. Or fusion is what stars do in their core, and fission is what we talked about last week with the alpha and beta and gamma decay. So stars run on nuclear fusion, and that's how it kind of relates here. So the first kind of star is a protostar, and a protostar is not a star because in its core it doesn't do fusion yet. That's the definition of a star. We define stars a lot based on what kind of fusion they're doing, and protostars aren't yet doing fusion. So where does a protostar come from? Well, in space, there's a collection of huge collections of hydrogen gas, and this hydrogen gas gets pulled together by gravity, and when gravity pulls things together, they exert pressure, and that pressure and that force makes it hot. So this is a hot collection of hydrogen gas that's being pulled together. It might even glow and emit some light, but it's not yet doing nuclear fusion, but it is on its way to being a star. It just needs to keep sucking in hydrogen, and gravity needs to keep doing its thing until eventually the cloud is all sucked together and a star is formed out of the middle of that.
Long before stars begin fusing hydrogen at their centers, when they are still just hot overdensities in the process of contracting, we call them protostars. Space is not that empty after all. It's actually full of gas and dust, which is called the interstellar medium. The gas is mostly made up of atoms of hydrogen, though small amounts of heavier elements can be found floating through space as well. In some regions, the interstellar medium is assembled into a big cloud of dust and gas called a nebula. Stars begin very small, simple particles in vast clouds of dust and gas. These nebulae remain cold and monotonous for ages until everything stirs up when a newcomer speeds through. As particles collide, they begin to form clumps. Eventually, a clump reaches more mass, and therefore a stronger gravitational pull, attracting even more particles from the surrounding cloud. Hence, the center grows denser and hotter, and over millions of years, the clump grows into a small, dense body called a protostar. A protostar looks like a star, but its core is not yet hot enough for fusion to take place. The brightness we observe comes from the heating of the protostar as it contracts. Protostars are very difficult to be seen in the visible spectrum because they are surrounded by dust and gas, which blocks the light they emit. This stage of stellar evolution may last for between 100,000 and 10 million years, depending on the size of the star being formed. Slowly, when the stellar winds and radiation blow away the gas and dust, and when the surrounding shell is all cleared up, the star will enter the T-Tauri phase, for which we will talk about more in the next video.
Alright, for your notes here, you're going to type all of what's in the PowerPoint. It's not that much. So like for protostar, you would type this sentence here into your CamiDoc. But here for the picture, this box here, you can grab your drawing tools and you can try and draw an approximation of a protostar if that's what you want to do. Or if you go to Add Media and then go to the one that says Google image search, and then just search for protostar. Then it will give you some options, and so I like this picture here. And then I just put it where I want to go, and then you can resize it and make it fit into the box here. So that's just an easier way of doing this assignment, or if you want to draw it by hand, feel free, but you do need to include a picture in addition to typing the information that goes here. So the next star is main sequence. So main sequence stars, our sun is a main sequence star. Main sequence stars are most of the stars in the galaxy. Most of them are on the main sequence. Our sun is also on the main sequence. Main sequence stars are in the part of their life where they are doing fusion now. So in the center of the core of our sun, it is doing this process called fusion, where you take hydrogen atoms and you crash them together at really, really high temperatures and speeds. And it's so high temperature and speed that they can fuse and form new atoms. And so hydrogen gets turned into helium in the core of the star. And this is where new atoms come from. This is where helium comes from. This is where, lithium, beryllium, even gold, they come from fusion inside of stars. Or later, we'll talk about the explosion of stars. So stars form new elements in their core, and a small amount of the matter from hydrogen into helium gets vaporized. So that's the equation that Einstein came up with, and you'll hear about this later in an Edpuzzle. But Einstein came up with the equation E equals mc squared, and E is energy, and m is mass, and c is the speed of light. So the energy that a star forms is when you take its mass and you multiply its mass times the speed of light squared, which is a huge number. So take a small amount of mass and multiply it by the speed of light squared, and you get a huge amount of energy. So a tiny amount of the matter from hydrogen, the electrons, gets vaporized and turned into helium. Along the way, you lose just a tiny bit of that matter, and that is where stars create their massive amounts of energy from. This is a picture from the Hubble Space Telescope. So this is a picture of galaxies. So you can see galaxies come in a lot of different shapes. And this is just to give you an idea of how big space is. So we are in one galaxy, a Milky Way galaxy, but look at all these other galaxies that are out there. And each galaxy can have millions of stars or billions of stars in them. And each of those millions and billions of stars can have their own planets going on as well. So just an idea of just how many different solar systems are out there. It is huge number. And you can see the different colors here as well. We're about to talk about different colors of stars. And you can see they come in different colors.
Once a protostar starts burning hydrogen in its core, it quickly passes through the T Tauri stage in a few million years and becomes a main sequence star. During this stage of our universe, the majority of all stars in our galaxy and the universe are main sequence stars, including our sun. These types of stars can vary in size, mass, and brightness, but the reason why all of them are considered main sequence stars is that they are converting hydrogen into helium in their cores, thus releasing huge amounts of energy. The tremendous amount of energy released stops it from contracting even more and causes it to shine. The fusion of hydrogen requires temperatures of more than 10 million Kelvin. A star in the main sequence is in a state of hydrostatic equilibrium. That is when the fusion reactions produce an outward pressure while gravity pulls the star inward. The inward and outward forces balance one another out, therefore stabilizing the star so that it maintains a spherical shape. How long a main sequence star lives depends on how massive it is. These stars can range from about 1/10 of the mass of the Sun to up to 200 times as massive. A star with the mass of our Sun remains in main sequence for almost 10 billion years, until all of the hydrogen has fused to form helium. A higher mass star may have more material, but it burns through it faster due to higher core temperatures caused by greater gravitational forces. A star 10 times as massive as the Sun will stick around for only 20 million years. Meanwhile, a red dwarf, which is half as massive as the Sun, can last 80 to 100 billion years, which is far longer than the universe's age of 13.8 billion years. This is why astronomers think red dwarfs are good sources for planets hosting life, because they are stable for such a long time.
Alright, so the next kind of star is a red giant. Here you have a picture of a red giant in comparison to our Sun. So you can see that it is a much bigger star. Someday our Sun, and we'll talk about this next week, but someday our Sun will become a red giant. And when that happens, Earth will be destroyed. So all of the planets up through Mars will kind of be on the edge here, right at the edge of the planet. All of the other planets will be eaten by the expansion of the Sun. And so why does this happen? Well, at some point in time, the Sun is going to run low on fuel, which is hydrogen, and it's doing hydrogen fusion. And so its core will become made predominantly of helium. And at that point in time, you're going to start to do helium fusion, where you fuse helium into carbon and heavier elements, and that causes an expansion of the star, and we'll talk more about why it's an expansion later, but that will cause the star to expand, so that's when it switches over from hydrogen to helium fusion.
Red giants are a state of stellar evolution beyond the main sequence life of a star. After billions of years of core nuclear fusion reactions, the hydrogen supply in the core of a main sequence star is exhausted. When a star exhausts this hydrogen in its core, fusion stops, and the star no longer generates an outward pressure to counteract the inward pressure pulling it together. Now, the core is degenerate ionized helium, surrounded by a shell of hydrogen fusion that continues the life of the star and causes the outer atmosphere to increase in size dramatically. The aging star has become a red giant star and can be 100 times larger than it was in its main sequence phase. The hydrogen-fusing shell eats through the surrounding atmosphere and deposits helium onto the shrinking core. The ballooning atmosphere cools down to around 3000 Kelvin, and the star takes on a redder appearance, hence the name red giant. In about 5 to 6 billion years, the Sun will eat all of the inner planets of our solar system and will reach the Earth's orbit, thus entering the red giant phase. With the star being powered by helium, its outer layers return to normal for a while, and it starts to shrink, get hotter, and turn a little bluer. It is believed that stars typically spend just 1% of their lives in the red giant phase. Some well-known stars in the red giant phase are Aldebaran and Mira. More massive main sequence stars evolve more quickly and further increase in size to become red supergiants, like Betelgeuse. The red giant phase of a star will only last a few 100 million years before it runs out of fuel completely and becomes a white dwarf.
Alright, blue giants. So they are the hottest stars. Hottest star color tends to be blue. You'll do an assignment this week where you classify stars based on their temperature and luminosity. But blue are the hottest stars. They have used up all of their hydrogen and they're now burning helium. They are more massive and they often start out as red giants, and then as they progress through their fuel, they get hotter and that causes them to turn blue. I don't really have a video about that. The only thing you need to know about blue giants is they're just like red giants, except they turn blue because they are hotter. And then white dwarfs. So at some point in time, you're gonna run out of fuel. So if you're a star like our sun and you've gone through the main sequence phase and then you went into the red giant phase and then you run out of helium fuel, the star collapses, the core collapses, and then it shrinks due to gravity. And so all that hot matter doesn't just go away, it sits there in this leftover core called a white dwarf. And so this is all just the leftover heat of a star that is no longer doing fusion.
White dwarfs are basically the burned-out cores of stars. The central region of a typical white dwarf star is composed of a mixture of carbon and oxygen, surrounded by a thin envelope of helium and an even thinner layer of hydrogen. When a star like the Sun, or with an initial mass of up to 3 or 4 solar masses, has burned off all of its hydrogen fuel, it expands to become a red giant. After the outward pressure from the fusion reaction stops, the star expels most of its outer material and creates a planetary nebula. What remains is the core of the star, which becomes a very hot white dwarf, with a temperature over 100,000 Kelvin. Because there's no fusion reaction happening anymore, unless it is accreting matter from a nearby star, the white dwarf cools and becomes invisible over the next billion years or so. This beautiful Hubble Space Telescope image shows a nearby white dwarf and the outer layers of the former star's atmosphere, which have been blown away, creating a planetary nebula called NGC 2440. White dwarfs contain about the mass of the Sun, but have roughly the radius of Earth, and that's why they are among the densest objects in space. A teaspoon of matter from a white dwarf would weigh up to 100 tons. According to NASA, the gravity on the surface of a white dwarf is about 350,000 times that of gravity on Earth, meaning a 150-pound person on Earth would weigh 50 million pounds on the surface of a white dwarf. When a white dwarf stops radiating and becomes a cold and inert stellar remnant, it becomes a so-called black dwarf. But because the time required for a white dwarf to reach this state is calculated to be longer than the current age of the universe, which is currently 13.8 billion years old, no black dwarfs are expected to exist in the universe now. However, if a white dwarf is part of a binary system, it may be able to pull material from its companion onto its surface. Thus, the added mass could cause it to collapse into a much denser neutron star, or even increase its temperature and trigger a runaway reaction that detonates in a violent supernova that destroys the white dwarf.
Alright, so the most common kind of star that exists in the solar system is a red dwarf. Here would be our sun compared to a red dwarf. It's a lot smaller, it's a lot cooler because it's red. Red tends to be a cool color. They have lower mass, they collected less hydrogen in the beginning of their life than other stars. And so because of their small size, they don't burn fuel as quickly, so they tend to last longer. This also makes them the most common type of star because they can live for trillions of years, so there are more of them that have existed, whereas stars like our sun, once they run out of fuel after a couple billion years, they become a different kind of star, whereas red dwarfs stay red dwarfs because they're still got fuel to keep going.
Red dwarfs are the most common kind of stars in our galaxy. A full 3/4 are red dwarfs, but they are too dim to be seen with the naked eye from Earth. A star's temperature determines how bright the star is and what color we perceive when we look at it. Stars like our sun, which are hotter and give off more energy, are white. The cooler temperatures of red dwarf stars mean that they give off less energy, and their light is reddish. These kinds of stars are the smallest of the smallest. They are between 0.075 and 0.5 of a single solar mass. So even at their biggest, they're only half the size of our Sun. Red dwarfs are the coolest main sequence stars, with a spectral type of M. They are much cooler than stars like our Sun, reaching about 3,700 degrees Celsius, compared with the 5,500 degrees Celsius of our Sun. Red dwarfs form like other main sequence stars in clouds of dust and gas drawn together by gravity. And when the material clumps at the center and it reaches the critical temperature, fusion begins. Red dwarf stars are able to keep the hydrogen fuel mixing into their core, and so they can conserve their fuel for much longer than other stars. Estimations indicate that some red dwarf stars will continue burning fuel for up to 10 trillion years. Dwarf stars seem to be especially likely to have rocky planets. Calculations show that there are 1 trillion planets orbiting around red dwarfs in our galaxy, including at least 100 billion potentially habitable Earth-sized worlds. Our closest neighbor, Proxima Centauri, is a red dwarf with at least one planet orbiting in its habitable zone.
Alright, so next we have neutron stars, and neutron stars aren't doing fusion like other stars. What happens to get a neutron star is you have to have a really, really massive star. So at least 2.1 times the mass of our Sun. It doesn't go out like a red dwarf, white dwarf progress. Instead, when it dies, this huge, massive star, when its core runs out of fuel, the core collapses and then immediately explodes, and that explosion is called a supernova. And then one of two things can happen depending on the size of the star. The leftover core stuff, because all of the electrons and protons would have gotten blown away, you're left over with just neutrons, incredibly dense object, these neutron stars, because it's just the neutrons left over from the atom of the star. So like one spoonful of neutron star weighs as much as a cruise ship, because you've gotten rid of all of that empty space in matter. So this is one of the results of a supernova, which is an explosion of a massive star.
Neutron stars form when a massive star runs out of fuel and collapses. They are basically the collapsed, burnt-out cores of dead stars. When a star between 1 and 3 times the mass of the Sun dies in a catastrophic supernova explosion, the remaining core becomes a neutron star. The power from the supernova that birthed it gives the star an extremely quick rotation, causing it to spin several times in a second. Neutron stars can spin as fast as 43,000 times per minute, gradually slowing over time. Neutron stars pack roughly the mass of our Sun into a region the size of Manhattan. At these incredibly high densities, you could tamp all of humanity into a volume the size of a sugar cube. On average, gravity on a neutron star is 2 billion times stronger than gravity on Earth. In fact, it's strong enough to significantly bend radiation from the star in a process known as gravitational lensing, allowing astronomers to see some of the backside of the star. Not only are neutron stars tremendously dense, they are also incredibly hot. Whereas a 1,000 degree Fahrenheit charcoal fire glows red, young neutron star surfaces are over 1 million degrees and glow in X-rays. They are highly radioactive and have incredibly intense magnetic fields. Astronomers consider them arguably the most hostile environments in the universe today. As its name implies, a neutron star is composed entirely of neutrons. This is because when the very central region of a massive star, the core, collapses, it crushes together every proton and electron into a neutron. When a star between 1 and 3 times the mass of the Sun dies in a catastrophic supernova explosion, the remaining core becomes a neutron star. But if stars are even more massive, they will become black holes after the supernova goes off.
So then the last kind of star here is a supergiant star. So they have to be 12 times larger than the sun. So really, really big stars. They can come in any color, red, yellow, or blue. They burn hydrogen very quickly. They run out very quickly. They then burn, helium very quickly. They run out very quickly. And then they explode. So these are stars that don't last very long because they burn through their fuel so quickly, and they explode, and one of the results, like we just saw, could be a neutron star, and the other one, depending on if they're really, really big, it could leave behind a black hole, and that's where black holes come from. And black holes are just regions of space that are so dense there's so much gravity there that nothing can escape the pull of a black hole. So these come from supergiant stars.
Supergiants are the largest stars in the universe. Not only are they the largest, they are also the most massive and most luminous stars in the universe. Supergiants can have masses from 10 to 70 solar masses and brightness from 30,000 up to hundreds of thousands of times the solar luminosity. Supergiant stars in general give off between 10,000 and 1 million times the energy of our Sun. They are anywhere between 30 to 1,000 times the radius of the Sun. These gargantuan objects are old giant stars that are nearing the end of their life. Betelgeuse is an example. A bright red supergiant star in the constellation Orion, visible to the naked eye, and with a diameter about 700 times that of the Sun, and about 15 times as massive. Unlike stars like our Sun, supergiants are consuming hydrogen fuel at an enormous rate and will consume all the fuel in their cores within just a few million years. This means these types of stars live fast and die young. Their lifetimes are only 10 to 50 million years, which is extremely short on the scale of stellar evolution. Supergiant stars are only observed in young cosmic structures, such as open clusters, the arms of spiral galaxies, and irregular galaxies. They are generally classed as being either red or blue. Red supergiants have a mass at least 8 times that of our Sun and are generally old stars that were once similar in size to the Sun. Blue supergiants, on the other hand, are considerably hotter than red supergiants, but generally much smaller, only about 25 times the size of the Sun. When supergiant stars die, they detonate as supernovae, completely disintegrating themselves in the process.